It's time travel. So students, lecture of gravitation is loading. So students, this was nothing else but just a funny teaser, right? So that we can make physics as much easy as we can, right? And as much as simplify, right? We can simplify these things and concepts, right? Or we can represent, we can keep these things into the most innovative and different way in front of you all. This was a kind of an attempt, right? So okay students, so as usual, this is Indrajeet Singh, right? First of all, I forgot. Hello bacho, Sat Sri Akal and Namaste from my side, right? So this is Indrajeet Singh, your own physics educator, welcoming you all to the most sensible platform, right? The platform for an aspirants, those who are preparing for the JEE NEET kind of the competitive examinations, right? And lots, as you all know, the PW is a box of surprises, right? We are going higher, higher, higher and higher, right? So this champion series is for JEE and NEET aspirants. It was started with units in measurement, followed by motion in 1D, and then we moved on to the motion in 2D, and slowly we reached right to the gravitation. Okay, so now today we are going to deal with the concepts of the gravitation. So let's begin with awesome visualization. Okay, see, it's a very simple thing. First of all, we are going to discuss out, right? See, in this chapter, right, we are going to see Newton's law of gravitation. Okay, with that, what will be the variation into the value of the G. After that, we are going to see some concepts of the gravitational potential, potential energy, the most important aspect on which, right, there is an highest possibility in exam, right? Okay, there is an highest possibility that some may come right from this concept in an examination. And finally, the Kepler's law, right? So this much stuff we are going to see in this session, right? Stay till end, as you are going to right, enjoy the each and every moment when you're going to stay till end. Okay, see, flow chart. It's a tradition. You always used to begin with flow chart, right? So let's start with gravitation. See, gravitation is having some history, right? It started from the Greek philosophers, right? They gave a philosophy that Earth is flat something, the same conspiracy, right? The same thing is going on till now also. Some scientists are behind, right, to prove that Earth is flat, right? Lots of question marks are there, but we are not going to into that much detail approach, right, regarding that statement. But like, if I'm talking about it, is having, this thing is having some history, Greek philosophers. Slowly we went on to some assumptions, right, that Earth is at the center and the rest of the planets of the solar system and rest of the astronomical objects are revolving around this Earth. And after that, right, it came, right, okay, the final what we can say, the assumption, which is almost correct also, that sun is at the center and Earth with all other astronomical objects, it is revolving around the sun. Okay, the latest stuff, right, says that sun is also revolving right around some specific center, right, of a Milky Way, right, or a galaxy, our specific galaxy, right? So this kind of things are, lots of theoretical assumptions are there, right? Okay, who one is correct, right? Okay, lots of assumptions are there. But see, Apart from this, right, the Kepler was a person who gave the 3 laws of the planetary motion. Right, among them we are having the first law, the second law, the third law. First law, second law, the third law. Right, law of orbits, laws of areas, laws of periods. Right, so this is the first part of a flow chart of a gravitation, that it starts with the Kepler's law. Okay, now let's move on to the next part. Right, Newton's law of gravitation. Right, Newton's law of gravitation, in which we are going to deal with the scalar form. Right, we are going to deal with the vector form. Right, with this we are going to deal with the superposition principle, and the same superposition principle into the scalar and the vector form. So this is the second part. Right, now with this Newton's law of gravitation, we are going to deal right with the gravitational field intensity. Right, what is an actual concept of the gravitational field? What is a gravitational field intensity? Right, what is a gravitational potential energy? Second, what is a gravitational potential? Right, what is the relation between the gravitational potential and field? Right, lots of this thing. Right, the work energy theorem plays a prominent role. Right, and this is the work energy theorem. Right, okay, this plays a prominent role, and with this, right, we are having the concepts of escape speed. Right, okay, this escape speed is kind of the launching of the satellite, right, polar satellites, geostationary satellites, all of these things are there. Right, okay, escape speed, but these all are the applications of work energy theorem only. Right, the total energy, right, of satellite. Right, okay, and after that lots of concepts of the binding energy. Right, geostationary satellite. Right, lots of things are there. Okay, so this is some external part, right, regarding it. So this is what an actual, right, flowchart of a gravitation. Flowchart of a gravitation. I'm moving aside. If you want to have a like snap of it, okay, then on the countdown of 5, 4, 3, 2, 1, that's it. Okay, so this was right, a flowchart. Now let's move on to the most important stuff. Right, we are going to begin with the Newton's law of gravitation with an awesome visualization in front. What it states, right, it's a very simple explanation, I must say. Any two object in a universe has tendency, sorry, not any two, any object, right, that is, let's summarize this thing. Any object in universe, right, has tendency to attract another particle. Right, suppose let us take an example. If Earth is there, Earth is having the tendency to attract Moon. Right, okay, like this way, any particle in the, you see, I'm talking about the particle, I'm not talking about any kind of the rigid body or any kind of a structural body, any kind of, no, I'm not talking about that body. I'm only talking about the smallest particle. It is having a tendency to attract another in the universe. Now that tendency of attraction, Newton defined it on the paper with some formulations. Right, what that? So for that, let us take another example. Right, suppose this is mass m1, right, this is mass m2. These are the two particles. M1 is having the tendency to attract m2, m2 is having the tendency to attract m1. Right, so this tendency acts in terms of force. Suppose they are, right, separated by the distance r. Right, they are separated by the distance r. Right, they are separated by the distance r. Right, now this tendency, let us take an example. This is the first particle, this is the second particle. This tendency is acting in terms of a force. This force is attractive in nature always. Right, this force is always attractive in nature. Right, So that force, it is known as gravitational force. In another sense, right, the Newton's law of gravitation states that the force acting between any two particles, force acting right between any two particles in the universe, any two particles, is directly proportional to product of their masses, product of their masses, and inversely proportional to, right, it is inversely proportional to square of distance between them. So this was this is a universal law. There is a difference between what the law is proposed and what actually the law, right, that is universally accepted. Okay, the thermodynamics law, the laws of thermodynamics are universally accepted, right? The law of the gravitation, it is the universally accepted, applicables, it is, see, value differs, but it is applicable to the all objects, that is all particles present into the universe. So that's why it is also known as a universal law of gravitation. The name itself states that, universally accepted law of gravitation, right? Right, what it states, as usual, the force that is acting between the two particles is directly proportional to the product of masses, right, and inversely proportional to the square of distance between them. And this force is always attractive in nature, right? There are some properties, there are some noteworthy points related to this force. That force is always attractive in nature, because this force, right, always represents a tendency of one particle to attract another. That's why it's always attractive. And some students might be having the question in their mind, nah, why? Because if we see the examples of the, right, electrostatic force, then we are having kind of two types of the tendency. One is having the tendency to attract another, and second one, right, to repel. But here we are having only one kind of the case, that is attraction. This force, sorry, we were having a glitch right now, okay, and it was a sudden cut, and backup also failed, right? So sorry for that. Okay, so let's resume this. Okay, so see, I was explaining about the every particle in a universe has a tendency to attract the another particle, and we gave an example. Suppose this is a particle of one mass m1 and m2, they are separated by the distance r. So the tendency of an attraction acts in terms of force that was expressed by the Newtons, right? And that statement states that force acting between any two particles is directly proportional to the product of the masses and inversely proportional to the square of distance between them, right? So if we are removing this proportionality sign, then we are getting the equation as g m1 m2 whole divided by r square, right? G m1 m2 whole divided by r square, where g is the proportionality constant, that is also known as gravitational constant, right? It is also known as the, right, the g is a proportionality constant, it is also known as the gravitational constant, whose value is 6.67 into 10 to the power minus 11, right? What is the value of g? That is 6.67 into 10 to the power minus 11, right, Newton meter square whole divided by kg square, right? This is the value of the gravitational constant. So this is what, right, the Newton's law of gravitation is all about. There are some limitations of the Newton's law of gravitation, there are some exceptions in it, right? There are lots of questions, how it is applicable into the vector form, what is in the classification, whether it is applicable to the rigid body or not. Suppose if it is in the universe, I must say, in the entire universe only particles are not present, na? There are also the structural formations, right? There is a presence of a structural formations, na? So in that case also this Newton's law fails, right? What about, right, the system that comprises more than two particles, whether Newton's law is applicable to them or not? Lots of things we are there, like we are having to discuss, right? So this is all about what the basic definition is. You can see it is in the visualization also. This is Earth, this is Moon. There is a kind of an attraction between Earth and Moon. Maybe value will be different, but there exists an attraction between the earth and the sun. Okay, so what actually the basics is all about the Newton's law of gravitation. Now, what about the classification? Okay, that thing we saw, it was completely about the scalar form. Now this is all about the classification. First, if I'm talking about the Newton's law, then we are having it into the scalar form. Second, to overcome one of the limitations of the Newton's law of gravitation, right, we are having the superposition principle, right? Again, I am repeating it. To overcome the limitations, one of the limitations of the Newton's law of gravitation, we are having the superposition principle, and that too even in scalar form, in vector form, right? So when we'll jump on to the superposition principle, before that we are going to discuss two important limitations of the Newton's law of gravitation. So now students might be having the thought in the mind, right, that sir, it is a universal law of gravitation and it is having the limitations also, right? So these two are both different domains. They are different domains, right? Universal law of gravitation, it doesn't mean it is not having any kind of the limitation, because we are not that much we are not that much knowledgeable to understand each and every aspect of the entire universe, right? Even we haven't explored only 1% of it, right? Not completely 1%. Then how we can be how we are that much sure that these laws are universally acceptable. Universally acceptable, it means right, what things are in our knowledge, right, these laws are applied to it. Our knowledge, it means knowledge of science and technology. Our knowledge, it means knowledge of science and technology, right? Okay, knowledge of science and technology. So it means it is having the limitation. Having a limitation, it is a different domain. Being universally accepted, it is a different domain, right? So this thing we are going to see into the scalar and vector form, and we are going to discuss two of the limitations, as I said before. Okay, and here let's move on to the vector form. Why there was a need? See, as I said before, physics is always all about the why and suppose. Why there is a need of a vector form? Motion is always analyzed with respect to the reference frame and with respect to the reference point, right? So is it sure, if I am defining the Newton's law of gravitation, the force acting between the two particles is directly proportional to the product of their masses and inversely proportional to the square of distance between them? Yes, it is true. But is it for sure that those two particles lies only on the x-axis? Either they lie only on the y-axis or on the respective z-axis? No. My answer is no. Those two particles can be in whatever point. They can be at any point right into the three-dimensional space. In universe, entire universe is divided in approximately 11 dimensions, right? Okay. So these two particles can be anywhere. Then how we are going to define that law? Suppose if they are right, if they are like distributed, two masses are right kept on the respective x-axis, right, on a respective y or z axis, then we can define it through the scalar form. But what about when they are distributed, where they are present at any position coordinate, right, or they are having any kind of the position coordinate in an entire three-dimensional system or three-dimensional Cartesian coordinate system? In that case, right, okay, if things are going on in 2D and 3D, vectors are needed, right? If motion is going on, see, here it is not all about the motion, right? But if things are going in 2D and 3D, right? If positions vectors are defined in 2D and 3D in Cartesian coordinate system, then yes, vector is needed. Vector is needed. So that's why we are in need of a Newton's law of gravitation in vector form. Suppose this is an x-axis, this is an y-axis. This is particle 1, this is particle 2, right? They are separated by the distance r1. but this is what the magnitude of a distance between them. If I'm talking about the Cartesian coordinate system, r1 is the position vector of particle m1. Similarly, R2, right, it is the position vector of particle of mass m2, right? R1 is the position vector of particle m1, R2 that is a position vector of mass m2, right? Position vector of mass m2. So this is R1, this is R2, the things are there. Okay, things are. Now, how we are going to see? The definition is going to be same. Force directly proportional to the right product of their masses. Yes, simple. Force, it is directly proportional to the product of masses, right, and inversely proportional to square of distance between them. This is in vector form, right? This is in vector form. So it means distance is also going to be in vector. Suppose this is a position vector of R1, right? Either it can be 2D and 3D, it's okay. This is a position vector of M2. So using the distance formula, we can calculate this distance R. So can I write it as R one minus R2 square. Now this is a vector, then we are having one unit vector, that is R12. This is how it is defined, right, into the vector form. This is how, right, the force is defined into the vector form. Now, evaluating this further, we are having force F, right, removing the proportionality sign, we are having G m1 m2 whole divided by R1 using the distance formula. This thing you have already seen into the mathematics, right? That is the distance formula. How I'm going to replace this stuff as R1 vector minus R2 vector. Why there is a need of a unit vector? See, whatever the force that is acting between these two particles, right? The force is a vector quantity. If you are defining, see, masses are the scalar, G is the constant, gravitational constant. If position coordinates are defined in three-dimensional space, obviously the force is going to be have, right, whatever the resultant force come between the two particles, right, it will have the components in x, y and z direction, right? So for that reason this unit vector is defined, right? Again I am having one question, whether I'm going to write force acting on 1 with respect to 2 or force acting on 2 with respect to 1, right? G m1 m2 whole divided by R1. Okay, the definition of the unit vector states that it is vector divided by its magnitude, right? That is R1 minus R2, right? So this is an actual formula, right? The expression of the Newton's law of gravitation into the vector form. Expression of the Newton's law of gravitation into the vector form. Now, what about force acting on 2? Suppose this is mass m1. This is mass m2. We are talking about an attractive force. The one, it is attracting towards 2. So this is force acting on 2 as because of 1. The 2 that is attracting 1, that is force acting on 1 as because of 2. What does this right expression says? Force acting on 1 as because of 2, it is attractive in nature. Force acting on 2 as because of 1, attractive in nature, right? So in this case, if I want to define it as F1 with respect to 2, then it is equal to G m1 m2, right, whole divided by R1 minus R2 whole to the power cube, and that is R1 minus R2, right? And if you want to write the statement of F2 with respect to 1, right, then I must say it is equal to negative of F of 1 with respect to 2, right, F2 with respect to 1 in terms of, right, okay, that is F1 with respect to 2 because the directions are reversed, right? The directions are reversed. Okay, so here we can't say this was just a simple explanation of a force into the vector form, and this is what the direction says, right? And this is what in a real explanation, whether m1 is going to attract m2. If m1 is going to attract m2, then, right, how force is acting, what will be its expression, and if m2 is attracting, it is having tendency, it is having the tendency, but if it is attracting m1 with a force F, right, then this is an expression for it. And as according to the Newton's third law of Y, right, see, you can just apply the Newton's third law here. They both are equal in magnitude but opposite in direction. Equal in magnitude but opposite in the direction, right? Okay, now, so this was the Newton's law into the vector form. Now basically, right, we are having the two limitations. First, it acts only, right, it acts only between the two particles, right? It acts only between two particles. So in entire system, right, is it possible there is only the presence of two? No. Infinite number of the particles are present in universe. Infinite number of particles are present in this entire universe. Then how? It is a universal law of gravitation. Then how we are going to define that stuff? Right? Second limitation. All objects in universe are only considered as particle they are not having any kind of the structural formations. Okay, none of the particle can be square, none of the particle can be perfectly sphere, none of the particle can be a hollow sphere. No. Is the particle is having any kind of the shape? If no, yes, it's okay, then it is easy, it is good to define the Newton's law of gravitation. But what happens, what in case of the rigid bodies, right? They are having kind of the formations, the structural formations, like what about a sphere, right? What about the, right, what we can say, the ring kind of the structure, right? We are not having any definite shape and bodies, right? We can't define that this much amount of this kind of only, sorry, we can't define that in entire universe we are having only specific things like particle. No, right? So these are the two most important, right, limitations, and they are been overcome, right? The first limitation, it is overcome by superposition principle. The Newton's law of gravitation states that this is particle of mass m1, this is particle of mass m2, they are separated by the distance r. The force acting between them is directly proportional to product of their masses, right, and inversely proportional to square of distance between them, right? Product of their masses and inversely proportional to the square of distance between them, right? Okay, what about the presence of third particle? Whether this force is going to affect in the presence of third particle or not, my answer is no, right? Okay, my answer is no. First point, the gravitational force acting is not going to affect in presence of third particle between two. The force between these two is going to be same only. This F12 or F21, it is going to be same in magnitude unless and until their masses are not getting changed or their respective distance are not getting changed. F is inversely proportional to r square. If masses are getting changed, right, then F is going to be changed. If R is getting changed, right, okay, then the F is going to change. This F value is not going to be changed, right, with the presence of the third particle. The resultant force is going to get changed with the presence of third particle, not the force. There is a difference. The resultant force is going to change, right, okay, in the presence of third particle in between two, not the force between first and second. It is going to change. So just keep this thing in mind. Now what actual the resultant forces we are going to discuss into the superposition principle. Don't get worried, right? Okay, so it is not going to, suppose this entire system is dipped into the water, whether this force is going to get changed? No. The gravitational force is not affected by surrounding medium, right? It is not going to affect by surrounding medium. Just keep one thing into the mind. The gravitational force is not going to, right, affect by the surround. Yes, but it is going to affect if the medium of the mass is getting changed. Okay, you can just understand this difference. Force directly proportional to product. If any, see, by any way, if M value is getting changed, F will change. But we are talking about the value of its own, not about the surrounding medium. Just keep one thing into the mind, right? Suppose, let us take an example. Density is equal to mass per unit volume. If I'm talking about a, right, sphere, density is getting changed, right? Volume is getting changed. Mass is constant, the force will remain constant. Mass is getting changed, volume is getting changed, right? Okay, suppose let us consider density of particle is changing. By any way, force will change, but density of surrounding medium is getting changed, force value will not get affected. That is a difference. The students are getting confused in this point only, right? If density of a particle is getting changed, how we can correlate this force to the density? We are going to see that stuff in sums also. Density of the particle is going to change. Yes, force will change between them. But density of the surrounding medium will change? No. If M and R is constant, yes, the force will remain same. So Fg is not going to affect by the surrounding medium. Fj is not going to affect by any presence of the third particle. This is not a force, but this is not the resultant force. This is force between two. Right? The force between two. So these are what the limitations, right? Third, second limitation. See, all objects are present in the universe. See, solution for this, right? Integration and the concept of gravitational field right, it is going to use the second, is used to overcome the second, right? The second limitation, it is going, it's this statement. Use of the integration and the concept of gravitational field intensity using Gauss law that you are going to see into the 12th standard, first chapter, electrostatics, right? That concept will help us in finding the gravitational force between the objects having any kind of the structural formations, or between the two objects or one particle or one object or one sphere, this kind of things, right? So to overcome this limitation, we are having superposition principle. To overcome this limitation, we are having the concept of the gravitational field intensity and the Gauss law. But practically it has been not defined, right? Okay, but we are having the concept of the gravitational field, right? Okay, practically we can't apply that Gauss kind of an or Gauss law of an electrostatics here, right? But there is an analogy to understand. At that point we are having the electric field, and here we are having the gravitational field, right? This kind of the stuff is always there. So this is these two limitations of the Newton's law of gravitation. Yes, in spite of being universally accepted, it is having the two limitations, and we are going to solve this stuff. And apart from this, by what factors this value of the force is going to get changed, right? So these are the two most important and noteworthy points, and based on this, questions in NEET and JEE examination has already been asked, right? Based on this statement, so that's why I kept in front. Okay, so you can just understand the flow of this chapter. First of all, we moved on to the theoretical aspect, what actually first it was considered and what actually now it is considered, right? All that heliocentric and geocentric stuff. First of all, we moved on to the Newton's law. We defined that stuff. Slowly we moved on to the classification, scalar, vector and superposition principle, and slowly we moved on to the some of the limitations statements. Now we saw the vector form, we saw the limitation. Now we are going to solve the first limitation, and that is the superposition principle, right? The superposition principle, right? Now let's see this stuff. Okay, what it states, suppose, right, in a system we are having more than two particles. Here Newton's law fails because Newton's law is only applicable for the two particles, right? So here the new concept of resultant force is introduced. We are not able to calculate the interactive force between, right, this particles present in the system. Why? Because Newton's law fails. Suppose let us take an example. This is particle 1, this is particle 2, this is particle 3, this is particle 4. With respect to particle 1, this is distance is r1, this distance is r2, this distance is r3, right? This distance is r2 and this distance is r3 and this distance is r1. So how I'm going to suppose if I want to calculate the force of entire system, I'm not able to do that because it is one of the limitations of the Newton's law, right? Okay, what it states we should only have two particles, and that should also, and they should also get separated by, they should be also, we are having the two particles and they should be at right some specific distance, right? Okay, they should be kept, they should be placed at some, they should be present at some like specific distance. But we are following some reverse, right, psychology. Like we are following, like we are approaching this into the different way. Can we calculate the resultant force acting on any one particle as of particles present in system? Select any one particle. There are some steps. Step 1. Steps. Select any one particle. Suppose we have selected one. We need to calculate the resultant force on this. Resultant force acting on one. The resultant force acting on one as because of another particles of the system. The resultant force acting on one as because of another particles of the system. Force on one. How many particles in systems are there? 4. Force acting on one as because of 1. Force acting on 1 as because of 2. Force acting on 1 as because of 3. Force acting on 1 as because of 4. Yes, we can do that. Directly we can't use the Newton's law of gravitation for the all particles present into the system, but indirectly, if we are selecting any reference particle, any one particle, then we are able to calculate the resultant force of all particles in the system on one specific reference mass. Suppose we selected step 1. We selected the mass, resultant force on M1 as because of remaining particles we need to calculate. So it's F1 is because of 1, F1 is because of 2, F1 is because of 3, and F1 is because of 4. Right? Can I replace this into the scalar form? G, see, F1 is because of 1, it is going to be 0. Right? Okay, so finally F1 is because of 2, 1 is because of 3, 1 is because of 4. The final expression, this is the resultant force, right? This is the expression of the resultant force, guys, right? Okay, there is a difference between, right, the resultant force and the force that is acting between two particles. The force is acting between two particles is Gm1 m2 by r square, but resultant force is having more than, it is having the presence of more than two particles into the system. This is what the resultant force is all about, right? So it's F1 is equal to G m1 m2 whole divided by r12 square plus G m1 m3 whole divided by r13 square plus G m1 m4 whole divided by r14 square. Right? This is what superposition principle is all about, and it is used to calculate the resultant force on any single particle as because of another. Right? In summarized form, it is used to calculate right, the resultant force on any one particle as because of others. Right? Now suppose I'm like another question I'm having in mind. If these particles are right, they are present at any position in the three-dimensional space, then how we are going to define? If it is going to overcome the one of the limitations of the Newton's law of gravitation, then yes, it is for sure it is going to overcome into the vector form also. Why? Because Newton's law is represented into the scalar and vector form both. Then limitation is going to arise in both of the cases. Right? Now, using the superposition principle, the same thing we are going to calculate, the same thing, right? We are going to do, right, into the vector form. Yes, we are going to calculate the resultant force into the vector. Suppose this is x-axis, this is y-axis, this is z-axis. 1, it is x-axis. 2nd, it is y-axis. 3rd, it is z-axis. Suppose this is a position, this is mass m1, this is mass m2, this is mass m3, this is mass m4. This is a position vector of particle m1, this is position vector of particle right, m2, that is r2, right? This is position vector of particle m3, right? This is r3, and this is the position vector of particle, right, m4, that is r4. Step 1. Select the reference particle. Again, I am taking it as a 1. We need to calculate the, right, the resultant force on. But this time it will be defined into the vector. As usual, F1 acting on 1 into the vector form, F1 acting on 2 into the vector form, F1 acting on 3 into the vector form, F1 acting on the 4 into the vector form. This will be 0, right? So the resultant force F1, that will be equivalent to F1 as because of 2, F1 as because of 3, F1 as because of the 4. So what will be the final expression of the superposition principle? G m1 m2 whole divided by r1 minus r2, right, whole cube, and that is r1 minus r2 plus G m1 m3, right, whole divided by right, r1 minus r3, right, whole cube, right, r1 minus r3 plus g m1 m4, right, whole divided by r1 minus r4, right, whole cube, right, and that is r1 minus r4. Okay, these calculations are going to be right. Okay, these are quite complex calculations, right? Okay, but you need to take care of, right, to get those answers correct, right? Okay, so this is what, right, the superposition principle into the scalar form is. Now let's see some of the examples, right, that has been already asked into the NEET examination. Some of them are asked, right? Okay, some of them I'm going to show you all in front. Two astronauts are floating in a gravitational free space after having lost contact with their spaceship. The two will what? Suppose, let us take an example. They were in the space and suddenly, this question has been asked in NEET 2017. Suddenly, right, there was a failure in one of the specific part, right, and those the astronauts have to do the space walk, right, and solve that problem, right. Obviously they're going to move out of this space, and suddenly, as of some solar storm or anything, right, they lost the contact, right. So in the entire space, one astronaut is at some x point, another like with the position of the first astronaut is some r1, right, position of the second astronaut is r2. Now they are not in contact with either with the spaceship, but there exists a mutual force of attraction. What is Newton's law of gravitation? What it states, right? It states that any particle in the universe is having the tendency to attract the another particle, right? So whether they are having the mutual force of attraction or not, yes, I can understand they are at the very large distances, right? See, right, I am completely aware of that F is inversely proportional to 1 by r square, right? It is inversely proportional to 1 by r square. Yes, I am aware of, but I can understand they are at the very large distances, right? So as of this inverse relation force, the mutual force of attraction, right, acting between them would be quite less, but quite less, it doesn't mean it is zero, right? So suppose this is a position of the particle, right, of the astronaut 1, right, and this is a position of the particle of astronaut 2. So there always exists the right mutual force of attraction between them, right? Okay, so keep floating at the same distances between them. Move away from each other will become stationary, wrong. Move away from each other, wrong, because this is an attractive force, right, not repulsive. They will move towards each other, right? They will move towards each other as because of, right, as because of their force of attraction, right, as because of their force of attraction. Two particles of equal masses are moving around the circle of radius r. Under the action of their mutual gravitational forces, the speed of the each particle will be what? This question is asked into the 1995, right? Okay. This is particle 1. Right, both are of the same masses. They are separated by the distance of r, right? It is what said na, radius of the circle r under the future. Okay, it is a radius of the circle r. Okay, I'm sorry, it is the radius. So it means they are identical particles, na? So they are separated by the distance 2r, and each one is moving on the circle r like this way. Right, like this way. This is moving with respect to this. This is a reference point O, with respect to point O, this particle M is moving like this way, this particle M is moving like this way. All right. One thing is sure, masses are identical and they are moving into the circular path. Now, the question arises, why they are moving into the circular path? Which force is responsible? Which force enforces the particle to move on the circular path? First point, as of the presence of centripetal force, they both are moving on circular path. Both are moving on the circular path. Right? As of the center. Now, the second question. Who is going to provide that centripetal force so that they are both are moving on the circular path? The mutual force of attraction between them. The mutual force of attraction between them. Second statement, the mutual force of attraction between them. This is going to provide the necessary centripetal for particles, right, to move on circular path. It means that whatever the gravitational force acting between them, it is equivalent to centripetal force. If these conditions are satisfied, right, so they can follow the specific circular path, right? So it means that what is N, the force of attraction between them, that is G m1 m2 whole divided by distance between them is 2r. What is the centripetal? Mass of first particle into velocity mv square whole divided by, what is the radius? Say distance between them is 2r. So Newton's law of gravitation deals with the actual distance between them. But if I'm talking about the centripetal, then it is going to deal with the radius of the circular path. So whenever we are dealing with the distance, it will be 2r. Whenever we are dealing with the distance, it will be r. So it is gm square whole divided by 4r square, that is mv square by r. What will be the velocity of the individual particle? It is 1 by 2 under root of gm whole divided by r. Right. So this is what an actual concept states. Right. How we can combine the concept of the centripetal, right, force and the Newton's law of gravitation to get the answer. The first one is a perfect answer for this specific question. The first one is a perfect answer. Two spheres. Again, the same statement. Two spheres of masses m and capital M are situated in air. First case, it is air, right? This is small m, right? This is capital M. They are placed, they are situated at the, let us take an example, at the distance r. Now the gravitational force acting between them is F. Obviously, it is for sure. The space around the masses is now filled. See, there is no change in the density of the particle. No. The density of the surrounding medium is getting changed. Air is now with some filled some liquid with the specific gravity According to the Newton's law, force is equivalent to G m1 m2 whole divided by r square. I want to just ask you all, m is getting changed with the presence of the, right, see, in the say if this entire system is dipped in some else liquid with some value of the density. Doing this, whether this small m is going to change, or this capital M is going to change, or this capital R is going to change, no. As I said, see, these two statements, right? Okay, second statement, the first statement, both are having, right? Okay, based on this already, right, some of the questions are asked, right, in exams. Fg is not it is not affected by the surrounding medium. Small m is not going to change, capital M is not going to change, right? The distance is not going to change, and how this force is going to be changed? This force will remain constant, and obviously, right, okay, the F will be the perfect answer for this. Let's take another example. Suppose this is M. Let's use some superposition principle and solve this term. Right, suppose this is M. These three particles are placed, right, on n vertices of an equilateral triangle. Right, side is R. Let us take an example. Side is L. Let's change this value as L. Equilateral triangle of the length L. Three of them are moving, right, on a circular path as because of the mutual force of attraction. What will be the velocity of each? What is our target? What is mentioned into the question? Three of the particles are placed on the vertices of the equilateral triangle. They are moving on the circular path, right? If they are moving on the circular path, it means there is a presence of the centripetal. Who is going to provide that centripetal? Obviously, the mutual force of attraction between them. And students are having their question, how these things are going, how they are going to follow the circular path. See, Jadoo. Like this way they are going to move. This mass will be having velocity like this way. This mass is going to have velocity like this way. And this mass is going to have velocity like, right? With respect to the centroid of the triangle, they are going to move. It means this is the radius and that is L by root 3. This distance you all are aware of, that is L by root 3. Right? Now, how we are going to, right, calculate the velocity? How? See, one thing we are sure. The resultant, the gravitational force, right, is providing the necessary centripetal. If this condition is satisfied, then and then the particles can move on the circular path. Right? First, we are going to see the case of the identical particles, and then we are going to see the case of the unidentical particles. M, then and then they are going to move on to the circular path. It's one and the sure thing. Right? But there is a presence of more than two particles. It means right here the superposition principle, this Newton's law of gravitation fails. Then how we are going to calculate this? If there is a presence of two particles, then the gravitational force between them is responsible for providing the necessary centripetal. But if there is a presence of more than two particles, then resultant force is responsible. Two particles, the mutual force of attraction is responsible for a particle. It provides the necessary centripetal acceleration. But, right, for more than two particles, the resultant force provides. Let's see how this resultant force. Okay, see, necessary, the resultant force, now we are all aware of the resultant force acting on this particle will provide the necessary centripetal. So, this is the force acting on 2s because of 1. This is the force acting on 2s because of 3. Angle between them is 60 degrees. The resultant of this force, right, the resultant of this force, right, it is going to see. The magnitude of the resultant force acting on 2 will provide the necessary centripetal. Right. I already told you the difference between, right, if it is a 2 particles, then it is a mutual force of attraction. If it is a more than 2 particle system, then we are having the resultant force. So how we are going to calculate this resultant force, right? One, it is F, this is F, they both are at the 60 degree. What will be the resultant? F square, right, plus 2F square cos of 60. So the resultant force, that is equivalent to what? Under root of 3F. And that is equivalent to, right, the centripetal, right? And this root 3gm square by L square. What will be the centripetal? mv square by R. What is the radius? That is L by root 3. What is the velocity? From evaluating this, we are going to get the velocity as under root of gm by L. Right? So what is an actual concept? Fg, that is equivalent to F of C. Right? Okay, Fg, that is equivalent to F of C. Now, till now we have seen the cases of the identical particles. Now let's move on to the cases of the unidentical particles. Suppose this is M, right? This is 2M. As because of the mutual force of attraction they are moving, then what will be the velocity of M and 2M? Sir, till now you only told us about the cases of the identical particles, right? And now you all are telling about the cases of the unidentical particles. Sir, it's wrong. Suppose if they are separated by the distance r. See, just keep one thing into the mind. If it is a case of the identical particles, it's okay, it is going to easily, right? We are going to resolve it easily. But if it is a case of the unidentical particles, right, they always move with respect to center of mass. They always move with respect to the center of, they always move with respect to the center of mass. So first of all, in this step, we need to identify, we need to locate the position of the center of mass. So let's use the concept of the center of mass, right? This is the reference point. What will be the position? That is m1 into 0 plus 2m into r whole divided by 3m. So it is 2r by 3. From this small m, the center of mass is at the 2r by 3 position, and from this we are having r by 3. With respect to this center of mass, right, they both are moving. Same concept. The gravitational force acting between them is providing the necessary centripetal. What will be the velocity of mass m? If I am talking about mass m, what will be the radius of the mass m? It is 2r by 3. Okay, see, gm 2m. This is a mutual force of attraction, right? I'm sorry. Okay, this is r square and this is m Vm square whole divided by 2r by 3, right? Okay, so this m is going to cancel, this r is going to cancel, right? So it is 2gm whole divided by r, that is 3vm square whole divided by 2. So it's 4gm whole divided by 3 of r. This is the velocity of smaller particle, right? Now what will be the velocity of the bigger particle, right? It is v of 2m. Same. The same concept we are going to apply, that is gm of 2m whole divided by r square, that is equal to tmv of 2m square whole divided by r by 3, right? So this 2 is going to cancel, right? So v of 2m, that is under root of gm whole divided by 3 of r. Okay. So this is what I mentioned. This is how. If they are two unidentical masses, then obviously they are going to revolve, right? They are going to move on the circular path, right? And the radius will be calculated with respect to the reference point, and they are going to, that reference point will be center of mass of the particles. Suppose this is a homework from my side. 4 identical particles are there. They are placed on the vertices of the right square of the length L. What will be the velocity of the each m? See, in the previous cases, if I'm talking about, right, see, you can understand. In the previous cases, right, see, if I'm talking about this case, then velocity is equal for 3 of them because they are the identical particles, right? Okay. And they, for them, the radius would be equal. And even the resultant force from the all particles is also same. But in this case, they are unidentical particles, so the radius for both is going to change. And as because of that, both are having the different velocities. One is twice with respect to another, right? So this is a homework from my side. Suppose this is M. This is 4M. They are separated by distance R. At what distance third particle is kept to make resultant force 0? At what distance? At what distance either from M or 4M? At what distance the third particle is kept? This kind of the questions are also there, right? And we are going to see that. Suppose let us take an example at the distance of x from the M and the distance of, right, r minus x from the 4M. Suppose here if the third particle is kept, suppose it is having mass m dash. So here the resultant force is 0. So it means the resultant force is 0. It means the force acting on m dash as because of m, that is equivalent to force acting on m dash as because of 4m. Right? If this condition is satisfied, then and then the resultant force is getting 0. In terms of vector, I can write this expression like this way. So g m dash m whole divided by x square is g m dash 4m whole divided by, right, r minus x whole square. So gm dash is going to get cancelled. 1 by x, that is equal to 2 r minus x is equal to 2x, r is equal to 3x, x is equal to r by 3. From m at r by 3 distance and from this at 2r by 3 distance, right, the resultant force on that point, on if we keep the m dash particle on that point, then the resultant force is going to be 0. Right? So this is all about the Newton's law of gravitation. Now let's move on to the most important aspect of variation of the small value of g. Variation of g, but what actually the g is all about, and how the value of the small g is getting changed. See, in our previous part, right, when we saw the Newton's law of gravitation, right, we dealt on with the factors on which the actual value of our force depends. As I saw, suppose the surrounding medium is getting changed, right, the force value is not going to get affected, right? But if there are any changes, see, if you are right, any change into the masses and the distance between the masses are noticed, right, then force value is going to get changed. So this is what the variation of g is all about. This is what the variation of g is all about. But what actual this g is? G is nothing else but a gravitational acceleration. G is nothing else but the gravitational acceleration, right? So what the gravitational acceleration is, how to calculate the, right, value of it. Suppose you can see this visualization, right? Suppose let us take an example at surface we are talking about, right? We are talking about a surface. Suppose if I kept, right, this is a right, the center of the earth. Let us take an example. It is a O, right? Okay, see, we saw the two limitations of the Newton's law of gravitation. Okay, first, right, it was completely about this one, right, or it was, yes, the to overcome the first right limitations of the Newton's law, right, we use that superposition principle. Now, this is important, right? Integration and concept of the gravitational field. What actual the gravitational field is, right? How using this integration we are able to calculate the force between them, between the one rigid body. Let's take an example for this. Always we are considering the earth as the spherical part. Suppose this is the earth, the one astronomical object. This is also the moon, right? Sphere. Both are sphere. They are separated by the distance r. How to calculate, right? These two are not particles. If distance, right, between two particles, it is very large as compared to the dimensions. If distance between the two particles is very large, right, as compared to the respective dimensions, then and then these two are considered as the particle. But, right, okay, this r, whatever the value of r is, it is not as much as, it is not reaching up to the infinite, so we can consider both as a particle, right? So these are the sphere, right? So for this kind of the rigid bodies, right, there is a different way for calculating the force, right? As they are separated, okay, so distance between the centers is calculated, is considered, sorry, not calculated, it is considered. Distance between their centers, O dash, right? Okay, the force always acts on the line joining between the two centers. Line joining the centers. Suppose if two particles are like this way, the force always acts right to the line joining the two centers. This will be the attractive force F and this will be the attractive force F, right? As this is one of the limitations of the Newton's law. See, suppose if they are separated by the distance apart, we can directly use to calculate, right? We can, right, directly use this formula F is equal to, right, G m1 m2, right, okay, whole divided by r square. But for that, right, we need to have some precautions, like distance between their centers are calculated, are always considered, and second, the force is always acting the line joining, on the line joining between the two centers, right? If for the spherical bodies separated by the distance apart, if we are using this formula, then these two things are needed to be considered. Now, what about this is an earth. Suppose if object is kept here, right, this is mass m, right? How? For this kind of the configuration, how we are able to calculate, right? For this complex things, right, the integration is needed, right? For this kind of things, right, using this two stuff, we can directly use this formula, right? Slowly and slowly we are going to clear up this concepts, right, and we are going into the deeper, right, of it. Okay, now see, so this were the limitation, right? So this is for the spherical objects, right, and the gravitational field nearby it, right? Suppose it is a kind of a, see, lots of things or lots of kinds of the objects are there, but especially we are dealing with the sphere, because all of those astronomical objects, theoretically we are considering it as a sphere, right? So now suppose, right, we are moving for how to calculate the value of the G. One object is kept at the surface of the earth. Obviously its weight is acting downward. Suppose, right, the particle is in equilibrium at the surface. Particle is in equilibrium at the surface. Particle is in equilibrium at the surface. It means its weight is balanced by some force that is the gravitational force, right? Okay, it is not like this way, right? Okay, if the particle is in equilibrium, right, its weight is balanced by, right, weight is balanced by the gravitational force acting between earth and that particle, right? It's, sorry, not upward direction, right? So here, what is the weight mg, right? Okay, what is the force acting, that is g small m, mass of earth whole divided by distance between the, right, particle and the earth, and obviously, right, it is r. Okay, the small m is getting cancelled, we are getting the small value of the g as g capital mass of earth whole divided by radius of the earth. This is the value of the gravitational acceleration. This is the value of the gravitational acceleration, right, at the surface. This is the value of the gravitational acceleration at the surface. But what actually this g means, at the surface particle is at equilibrium, its weight is balanced by, right, its weight is balanced by some attractive force that is acting between the earth and this particle. Right, its weight is balanced by the, right, the attractive forces acting, attractive force between the earth and that particle. Suppose if it is released, obviously according to the Galileo, it is going to accelerate downward towards the earth with the constant acceleration g, the g that we have seen into the third chapter, motion in 1D, motion under gravity, the same g I am talking about. Initially, the particle is at the equilibrium. Its weight is balanced by the gravitational force acting between the particle and the earth. Suppose if it is released, obviously it is going to accelerate downward. Yes. With what acceleration? With the constant acceleration g that is going to, right, fall. Right. And that will be g, this way. So at surface, we are having the value of the g as g capital M E whole divided by R E square. In third chapter, right, in spite of having the free fall, we were not considering any variations in g. But actually this value of g gets changed. See, this value of g is directly proportional to mass of earth and it is inversely proportional to r. If r is getting changed, g will get changed. If mass is getting changed of earth, g will get changed. Right? So this is an important surface, right? Sorry, it is an important stuff. How the value of the g is getting changed, right? Suppose let us take an example. This is at the surface I am talking about. If the particle is raised to some height h, are we having the same value of the g that we are having at the surface? No. Because distance with the respect to the center of the earth increases, g will decrease as because of the inverse relation. Suppose of any situation, this is not a earth, some else planet whose mass differs as compared to earth. Then at the surface we are going to have the same value of the g? No. Suppose let us take an example, this mass is released from the top, right, and it is reaching some at depth d, right, with respect to the surface of the earth. Then also we are going to have the same value of the g? No, things will get differ. Why? Here the distance is getting decreased, obviously g value will increase. It is for sure. See, we are not having the large variations in g, no, right? Okay, and there is a graph also for that, but it's okay. Variations in g are measurable with respect to surface, right? So it means, right, in third chapter we were considering all of those things as a particle, right? At that time we were not dealing with, right, the earth part, right, the earth factors. At that time we were not dealing with the force, right? So in kinematics, we were not interested into the cause of motion, that is force. That's why we are considering everything, the G as constant. Yes, it is 9.8. To ease those calculations, we were taking it as a 10. But now we are dealing with the force, right? It means whenever we are dealing with this kind of this stuff, so whatever the variations in G are measured, they need to be considered. Whatever the changes are there, we need to consider all of those factors. Classification. How G varies? First, with respect to surface or with respect to C. G varies with respect to mass and densities of the planet. G variation with respect to height from the surface of the earth, right? G with respect to the depth with respect to surface of the earth. These are the three factors with respect to which the value of the G is getting changed. This is only the reference thing. Whatever this formula we are getting, now we evaluated using the example of Earth, as obviously we are living on Earth, that's why. Right? Suppose it would be some else planet with a different mass, with a different radiuses, value is going to be different. I'm talking about the mass, G is different. If I'm talking about the Pluto, G is different. If I'm talking about the Mercury, hell sir, we are not going to stand on the surface of Mercury. I know that, right? I know that. So you can just understand all of these things, right? You can just understand all of those things. This is a common formula. Kind of variations we are going to have, these things. Let's see this and right. What is the formula of G? First, G with densities. G that is equivalent to capital G mass of Earth whole divided by radius of Earth square. Always, we are always considering Earth as a spherical object. Always consider sphere. It means how much mass that is contained in entire sphere will define its density. Mass contained in entire volume. Suppose this volume of the sphere is given by 4 by 3 pi r e cube. So the mass of Earth, can I say density into 4 by 3 pi r e cube? Can I consider this as equation number 1? Can I consider this as equation number 2? Replacing 2 in 1. Right. We are getting the value of the gravitational acceleration as G. G into density into 4 by 3 pi r e cube whole divided by r e square. This thing is going to cancel, right? Okay. So this small value of the G, that is equivalent to, right, G into rho 4 by 3, right, pi, okay, r. 4 G rho pi r by 3. This is what variations of G with respect to densities of the planet. G is directly proportional to rho r. G is directly proportional to rho r. If density of the planet is getting changed, the radius will get changed, G will get changed. Right? Keeping the mass as constant. Right? Everything is between density, mass and radius. See here. Density is equal to mass per radius cube. Right? Directly proportional. Right? Okay. So everything depends. See, if you are keeping mass constant, then obviously density and radius has to change. Right? Okay. To balance this stuff. Right? Density and radius has to change to balance the stuff. It's a very simple thing. Density and radius has to change to balance the stuff. Right? Now, see, it's a very simple thing. G is directly proportional to rho r. G is directly proportional to rho r. Now, let's see what happens. So, this was the first variation. right? Okay. Value of the gravitational acceleration of the earth, it is gme whole divided by re square. Another formula we saw, it is 4 by 3 pi rho gr. This is the variation of the g with respect to density. Suppose as of some reasons, right, as of some reasons, right, let us take an example of another planet, some x planet, right? For another planet I'm talking about, right, the value of the g acceleration for its 4 by 3 pi rho g of r, g dash r dash. For this planet, right, the density is twice the density of earth. For this planet, radius is twice the radius of earth, right? Then what will be the gravitational acceleration of that planet with the n factor, the gravitational acceleration of the earth? What will be the value of n? Density is twice. What is the value of the gravitational acceleration of the earth? 4 by 3 pi rho gr. Gravitational acceleration of the another planet, 4 by 3 rho dash g r dash, right? Let's evaluate this stuff, right? So it's a g of planet, that is 4 by 3 pi, right, rho dash g r dash. Can I say it as 4 by 3 pi density of planet, g radius of planet? So it is 4 by 3 pi. What is the density of planet? Right, it is twice the density of earth, right, and g twice the radius of earth. So g of planet, that is equal to 4 times into 4 by 3 pi rho g r. This will be the gravitational acceleration of the earth, that is 4 times g. This kind of the questions are always asked in examination, right? This is a comparison between the earth and another planet. In some circumstances, right, the value of the density of the earth is also getting changed. In that case also, we are also we used to, right, we used to evaluate the sum using this this formula. With respect to the surface of the earth, how the value of the g is changing while moving upwards? If I'm talking about the surface, what will be the value of the gravitational acceleration of the earth? That is g m whole divided by r square. Suppose we are moving at some height here. What will be the gravitational acceleration at that height? Can I say it is g of h, that is equal to g of m whole divided by r plus h whole square? Can I consider this as equation number 1? Yes. Can I consider this as equation number 2? Yes. We are going to resolve this thing. What is our motive? Motive to calculate the gravitational acceleration at the height h. And this also we are having two possibilities. What are those? We are going to see. But first of all, let's evaluate the basic formula. So g of h, that is equal to g of m whole divided by, that is r of square, that is 1 plus h by r whole square, right? Okay, this part is gravitational acceleration as at the surface, right? So can I rewrite this term as gravitational acceleration at height, that is gravitational acceleration at the surface, into 1 whole divided by 1 by h by r whole square, right? Okay, this is the actual formula. In another sense, we can also write this statement: gh is equal to g 1 plus h by r. I'm sorry. This is a general formula. Always we have to use this formula only unless and until one special condition is mentioned in the question. All the time we have to use this formula. But suppose if, right, h is less than r. The value of the h is very less as compared, right, to the surface of earth, right? Then using the binomial expansion, we are getting the value of the gravitational acceleration at the height at g 1 minus 2h by r. The rest of the terms of the biology, see, if h is less than r, right, then after this we are having the lots of terms according to the binomial expansion, right? But those terms will be quite less as compared to 0. Very, not less as compared to, but it will be very nearer to 0. So in that case we can avoid these terms, right? And in physics also, whenever you are using the binomial expansion, the simple thing you have to do, you have to just multiply this factor in front, right? You have to just multiply the factor in front and the case is resolved, right? You have to just multiply the vector in front and this case is resolved. So we are having the second formula, g at height, it is 1 minus 2h by r. So whenever nothing is mentioned into the question, we have to use the general formula. When h is less than r, we have to use this formula, simple thing. So this is what the value of the g varies with respect to the height, right? So we are having two formulas, are simple. Say students used to get confused in this stuff, right? Okay, they always use this formula. Actually we have to use this one. But when condition is satisfied, h is less than r, we have to use this. How g with respect to the surface of the earth, it is varying with respect to depth. How g with respect to the surface of the earth, right, is varying with respect to depth. At surface, we are having the value it as g capital M whole divided by r square, right? G capital M whole divided by r square. In this case, I want to tell you all, right? In this case, I want to tell you all that suppose if the particle is at this position, when it was at the surface, the gravitational force acting between earth and the particle, right? Okay, so the gravitational force was as because of entire earth when the particle is on the surface or in space. But when the particle is inside the, right, inside, and what happens? The gravitational acceleration, the force is acting as upon for this much part of the earth. So at that case, right, this g, okay, we are having the variation of the g as the, right, this side, variation of the g at the depth. We are having, this is a mass m dash of the earth and this is the whole mass of the earth, right, whole divided by, right, this is the radius of the earth and that is r dash square. Now as density of the earth is constant, right, density of the earth is constant, right? Now what we are going to see, density of the earth is got constant, so mass per unit volume of the earth, that is equal to m dash by v dash, that is density and that is constant, right? So in this case, if I'm talking about this r dash, can I say it is re minus d, right? Can I say it is re minus d? Yes, I can see that because this much is a d, the entire thing is r, right? This thing is r, this entire thing is r, right? And this much is d, so this part will be r minus d. So in this case, what will be the value of m dash? That is m into m into r dash cube whole divided by, right, r cube. Okay, and replacing the same here, the value of the g at the depth, right, okay, we are getting it as a, okay, g m dash, it is g, what is the value of m dash? M r dash cube whole divided by r cube into r dash square. So this thing is going to cancel, right? So g at the depth, we are having g of m whole divided by, right, it's r cube, right? So it's r cube, okay, and this is r dash, and that is re minus d. Further on resolving this thing, we are getting the gravitational, see, let us take g r square re minus d by r, right? So finally resolving this, we are getting gd as gravitational acceleration at the surface 1 minus d by r. This is the formula. We are not having any kind of the second formula for that, only one formula, right? Only one formula of that, right? So we saw the three kind of the variation. There is another variation, right? How the value of the g is changing with respect to latitude, right? So for all of those cases, I'm giving you direct formula. The first one, right, for the height, we are having the two formulas. First, the general formula, that is equal to g at the surface 1 plus h by r whole to the power minus 2, right? If h is less than r, right, then we are having gravitational acceleration at the height surface 1 minus 2h by r, right? Second, at the depth, right, we are having the gravitational acceleration at the d, and that is surface 1 minus d by r. Second, the third case, as see, this is now as because of the latitude, as because of the, suppose this is the earth, whenever we are moving on from the right poles, sorry, whenever we are moving on from the right equator to poles, I'm sorry, this is from equator, right, and we are moving on to the poles, right, with respect to lambda. At equator, lambda is 0, at poles, the lambda, that is equivalent to 90 degree. So for this, right, with respect to latitude, g minus omega square r cos square lambda, these are the variations of g, right? Okay, and in which omega is the angular velocity of earth or planet, angular velocity of earth or planet, right? So these three important formulas are there. Now let's see, right, you can have a snap of it, right? I'm moving aside, and with this we have seen the densities also, but density more than that, that these things are important. Okay, now I'm moving aside, you can have a snap of it on the count of 5, 4, 3, 2, 1. In NEET 2070, right, one question was asked. The acceleration due to the gravity at height 1 kilometer above the Earth's surface is at depth d. This is the Earth's surface. From here, at the height 1 kilometer is the same at the depth d. Right? Okay. Now see, you can see this 1 kilometer. What is the radius of the Earth? The radius of the Earth is, right, 6400 kilometer. Now what actually the height it is given 1 kilometer. Can I say h is less than r? Right? H is 1 by 6400th times less than r. Right? Okay. So in this case, at the height and the depth, right, the gravitational accelerations are same. So now here we have to consider, see, indirectly it is not given h is less than r, but we can see this. We can see this data. It is actually less than r. That's why we are using this formula. Right? So it is gravitational acceleration at the surface 1 minus 2h by r. That is gravitational acceleration of the surface 1 minus d by r. Right? Comparing this stuff, we are getting d is equal to 2h. So it will be 2 kilometer. So at the depth of 2 kilometer and at the height of 1 kilometer, we are having the same value of the gravitational acceleration. Right? With respect to the surface at the depth of 2 kilometer and with respect to the surface at the height of the 1 kilometer, we are having the same value of the gravitational acceleration. C is the perfect answer. If mass of the sun were 10 times smaller and the gravitational constant were 10 times larger in magnitude, mass of sun were 10 times smaller right? Mass of the sun is 10 times smaller and the value of the gravitational constant is 10 times larger in magnitude, right? Which of the following is not correct? See, in NEET 2018, this kind of question was asked, right? On the variation of G. Yes, it's important. What is the value of the gravitational acceleration? G is equal to, at the surface, if I'm talking about G, m whole divided by r square, right? If, see, if mass of the sun were 10 times smaller, see, we are having the raindrop will faster, walking on the ground would become more difficult, time period of the simple pendulum of the earth would decrease, and G on the earth will not get changed. So very simple thing, right? Very simple thing it is, right? Mass is getting, see, mass of the sun, it is getting m by 10, and gravitational acceleration G dash is getting 10g. What will be the gravitational acceleration formula? It is G dash m whole divided by r square. So can I say gravitational acceleration, right? I'm sorry, my mic, hello, mic G, hello. Oh, okay. Yes. So gravitational acceleration, that is equal to 10 g m whole divided by r square. See, so the gravitational acceleration G dash, that is equivalent to 10g. It is increased. Gravitational acceleration, it is increasing. It means that, suppose if I'm weighting 10 kg, right? Okay. My value of the G is getting increased. Mass is suppose 10 kg. What will be a weight? 100 Newton. If we are taking the value of the G as 10. Now, the value of the G is getting 10 times increased. So now suppose if mass is 10, then weight is 1000. In previous case, weight was 100. Now weight is 1000. Right? Now what will happen? Right? If weight is increased, obviously raindrops will fall faster, right? Because whatever the drop that is falling, it is a free fall, right? It is falling under the constant acceleration, and that value is increased, so it will, right, fall faster. Yes, obviously, A is the correct answer. Walking on the ground would be difficult. Yes, my weight is more. It is quite difficult to walk. Yes. Time period of a simple pendulum on the earth would decrease. Yes, T is directly proportional to under root of L by G. G will be high, T will be less. We have to select which is not correct. Yes, value on the earth, yes, will not get changed. See, value on the earth will get changed because here with the mass, the gravitational constant is also getting changed. That's why. Right? Let's move on to the next sum. A spherical planet has the mass m and diameter d. A particle of mass m falling freely near the surface will experience an acceleration due to gravity s. Right? See, acceleration due to the, see, this is r. It is g m whole divided by r square. So gravitational acceleration g m whole divided by d by 2 whole square. So it is equal to 4 g m whole divided by d square. This is the value of the gravitational acceleration. A is the perfect answer for this specific, right? Imagine a new planet. Oh, wow, equation of density is going to get come. Imagine a new planet having the same density as that of the Earth, but it is 3 times bigger than the Earth in size. It is 3 times bigger than the Earth in size. If the acceleration due to the gravity on the surface of the Earth is g, okay, then the surface. See, this is what the comparison between the planet and the Earth. See, equation of the g with respect to density, it was 4 by 3 pi rho g of r. Right? For a planet, let us take an example. This is for Earth. For a planet, it is equal to 4 by 3 rho g of planet. It is rho of planet g and r of planet. Yes, g is constant. Same density. Density is same, but it's 3 times bigger than the Earth in size. Right? It's a very simple thing. If density is same, then G is directly proportional to R, right? If density is same, then G is directly proportional to R, right? I'm sorry, I need to adjust this mic. Density is same, then G is directly proportional 3 times that of the R. So can I say G of planet by G of Earth, that is radius of planet by radius of Earth, right? So G of planet, that is equal to, what is the radius? 3 times the radius of Earth, right? Then this is gonna be G of Earth. So what is G of planet? This is 3 times G of Earth, right? 3 is a perfect answer. Simple. The density of the newly, this you all can do that. It's not a big deal. This is a homework from my side. You can answer all of this stuff right beneath the video, right? Okay, you can answer all of this stuff right, okay, beneath the video. Okay, the height at which weight of the body will becomes 1/16th, right? Weight at what height will become 1/16th weight on the surface? NEET 2019 latest question. Weight at the height, G at the surface, 1 plus h whole divided by R, right? Minus 2, that is equal to 1/16 weight at the surface, G, right? Okay, so this mg is gonna cancelled. So we are getting 16, that is equal to 1 by h by R, right? Whole square. 4, that is equal to 1 by h by R, right? And we are getting h value as equivalent to 3. So at the height 3R, right? Okay, we are getting, right, our weight, okay, to be reduced by 1/16th. Weight to reduced by 1/16th. Okay, so this was all about the gravitational acceleration. Okay, this question, right, variation of the G has been asked in mains 2000. And again, this is a homework from my side, right? Okay, homework answers you can answer beneath the video, right? You can comment, right? Your comments are most important, right? Okay, please do not ignore all of those stuff, please. I used to read all of those comments, right? And I really appreciate your love that you showered. Okay, so let's move on to the next topic, that is gravitational potential energy. Gravitational potential energy. So after moving on from this part, the variations in G, now let's move on to the most important concept of the gravitational potential energy, right? On which, okay, this is quite important because, right, the work energy theorem is followed, right? After this, we are going to discuss the work energy theorem, and it is even the most important part. Okay, so what actually the concept of gravitational potential energy states? I'm sorry about that, right? The gravitational potential energy, very simple thing, and a very simple classification I want to tell you all. Suppose this is an Earth, right? Before moving on to the concept of the gravitational potential energy, in short, right, I'm going to discuss the concept of the gravitational field. Around the Earth, there is a spatial area. Around Earth, there is a spatial area up to which the gravitational force of the Earth acts. That spatial area, it is known as gravitational field. One thing is also sure, this is not a fixed boundary. We can't say after moving 1 lakh kilometer away from Earth, we are out of its field. No, it's not like that. While moving away, far away from the Earth, the value of the gravitational force decreases like this way. The graph is like this way. It means value is getting, see, if you are moving 1 lakh kilometer away, 2 lakh kilometer, 10 lakh, 1 million kilometers away, right, 2 millions, 100 millions kilometer away, the value of the force is getting nearly equivalent to 0. The value of the gravitational field is getting nearly equivalent to 0. right? Theoretically, we are defining the boundary around Earth, right, up to which the gravitational force of Earth acts. That is gravitational field, simple terms. How gravitational field is going to help, right, in defining the stuff. Suppose Earth, infinite point, right, one test object of mass m is kept, right, one test object of mass is kept. There is one external agent, external space agency. We have given the task to external space agency, right? What kind of the task? This external space agency has to do the work such that to bring the object from an infinite position to any point under the gravitational field of the Earth by what so path, right? We have given the complete liberty, freedom, whatever you want to do, right? I have given that this space agency, you have to bring the object from here to here. That's it. Whatever you want to do, come on, move and do the task. Here comes the concept of the potential energy. Now space agency will do, he will grab this object and is moving nearer to the point P, and nearer to the point P. Now he is also smart. Space agency is also smart. Safely he is moving. He is moving with the constant velocity. He is moving such that the kinetic energy of the particle is not getting changed. He reached to the infinite position, grabbed that object, right? Okay, suppose he is NASA. He got a news at the infinite position, we are having the new mineral, right? Okay, new mineral is found, a new element is found. He immediately went to the infinite position, he grabbed that element, he took some samples, now he's moving back. Now he's doing safely. There might be presence of some alien civilization. We have to keep that sample, we have to write that we have to keep this sample safe because we need to drop this down to the Earth. So slowly, right, being in the, right, like he is completely in alert mode and he's moving. So he's moving in such a way that velocity of the particle is kept. The ex-alien civilization is having that type of the device, right, which can track the change in velocity of the particle. So this space agency is aware of. They is saying we have to move like a way that the velocity is constant so that alien civilization shouldn't get alerted and can attack on us. No. So he is doing the work against the gravitational field of the Earth. This kind of the work is always stored in the form of the potential. See, work done in bringing an object, it is always stored into the form of the potential energy that is defined as the gravitational potential energy. In summarized form, whenever an external agent brings the mass from the infinite position to the point under the gravitational field such a way, if external work is doing, see, if external agent is doing work, then it always comes with the constant velocity. If Earth is attracting, then velocity may get changed. Two different things. As of attraction it is coming, velocity may get changed. As of attraction, suppose Earth is attracting, right, and we are रास्ते से जा रहा था, भेलपूरी खा रहा था, smell attracted me, so our velocity got changed. Then velocity may get changed. But as of external agent, as of some Velocity will not get changed. In both of the cases, work is done. Right? And work is done either, see, whatever work is done either in support of the gravitational field or in opposing the gravitational field, it is always stored into the form of the potential energy. Work done is stored into the form of the potential energy, and specifically we can't define whether it is going against or in. Simple work done, right? Okay, simple work done that is stored into the form of the potential energy, right? Now that will define the concept of potential energy, right? Energy required to bring an object test mass from infinite to a point field of the earth. This energy, it is gravitational potential energy, and it is mass of earth, mass of object whole divided by r. This is its formula. There are some noteworthy points related to this gravitational potential energy, right? What are those noteworthy points? Let's see this. First, the value of the gravitational potential energy is always negative. What does the formula states? G capital M small m whole divided by r, where r is the distance between the test mass and the earth, right? Okay, suppose this is an earth of mass capital M, this is a small m, right? And they are separated by the distance r, right? Then this is the formula. So in this potential energy, the gravitational potential energy is always negative. The maximum value of the gravitational potential energy is 0. The maximum value of the gravitational potential energy is 0. It is always calculated with respect to the reference point. This thing we have already seen into the work, energy and power, right? Okay, when we were dealing with the concept of the MGH, you remember that was like, it was also gravitational potential energy, right? We were everything we were evaluating with respect to the reference point. Here also, right, the gravitational potential energy is always calculated, right, always calculated with respect to the reference point. In this case, in case of work, energy or power, we were taking ground as the reference point. Here we are taking the infinite position as the reference point. At infinite position, right, the gravitational potential energy is 0. Right. So these are some noteworthy points related to the gravitational potential energy. Right. These are some noteworthy points related to the gravitational. Now this gravitational potential energy, if you want to take a snap of it, you can have it on the countdown of 5, 4, 3, 2, 1. Classification. It is defined for the masses and system of masses. It is also defined for the rigid bodies. Let's see this directly. Let's see this, right? Because this is the concept where we are going to solve the sums, and right after this, the work energy theorem is going to come, and we are going to see that also. Okay, see the work done to raise a mass m from the surface of the earth. This is the surface of the earth. From center of the earth, distance is calculated. See, work done to raise a mass. This statement says that work is done by external agency, right? So it means work is done such a way that velocity of the particle is getting constant. So it means that change in kinetic energy is 0, right? So whatever the work will be done, it will be changed into the negative. potential energy. To raise a mass from surface of the earth, right? To raise a mass, here negative will be not there because the work is done against the field. Surface of the earth to height h. This is an initial position, right? And this is the final position. And this is also r. So what is the work done? That is change in potential energy, U final minus U initial. Final we are having position G m whole divided by. Distance is always calculated with respect to the center. So final position is having 2r distance with respect to center. So it's negative of 2r, right? And minus, that is minus G m whole divided by r. So the work done, that will be equivalent to G capital M small m whole divided by 2r. That is equivalent to mg r by 2. D is a perfect answer. Simple calculation. A body of mass m placed on the earth's surface which is taken from the earth to the height of h 3r. Very simple. This is an earth surface, right? This is an earth surface, right? This is height r. A body is kept at the earth's surface, right? This is an initial position, right? From this it is brought, right, to the height 3r from the earth's surface. So this is a distance 3r and this is the final position. How much amount of the work is done? Or you can say directly they have asked what is the change in the gravitational potential energy. That is same, work done by the external agent, right, in such a way that the velocity of the particle is kept constant. Right, so this will be the final, it is minus G capital M small m whole divided by 3r plus r 4r, right, plus G m capital M whole divided by r. So final it is 3G capital M small m whole divided by 4r. Right, so this will be the change in potential energy of the particle. See, 3 by 4 mg r. Right. So these are the sums related to the gravitational potential, right, energy. Now let's move on to the most important concepts of work energy theorem. Right, it reminds us about the chapter 6. Right, it reminds us about the chapter 6. Right, apart from this, we can even calculate, right, about the gravitational potential energy also. Right, suppose I'm giving you some extraordinary sum. Four masses are kept on the vertices of the square. Or if you want to simplify this, right, okay, 3 masses, right, are kept. If you want to simplify this stuff, right, and understand this concept, 3 masses are kept on the vertices of the equilateral triangle of length L. How much work is needed? How much amount of the work done by the external agent is needed, right, to make the configuration like this way? Twelve. This is mass m. This is an initial configuration, right, and this is the final configuration. How much amount of the work is needed, right, by an external agent to convert this system, to transform this system from a equilateral triangle of length L to 2L? So what will be the work done by external agent? That will be change into the potential energy. So that will be U final minus U initial, right? It's a very simple thing. Final, right? See, if we are having, right, the system of masses, then we need to calculate the number of the pairs of the gravitational potential energy by this formula. Number of pairs of the gravitational potential energy by this formula. Number of pairs, right? 3 particles are there. So it's 3 into 2 by 2. 3 pairs of the potential energy will be there, right? Like if I'm talking about the initial situation, right, and final, right? This is 1, this is 2, this is 3, right? So resultant potential energy of the system will be 1, with respect to 2, 1 with respect to 3, right? And u2 with respect to 3. Suppose there are 4 particles, 4 into 3 by 2, right? 6 pairs will be there. 5 particles, from this we will get a number of pairs. Number of the pairs, we see 1, 2, 3, 3 pairs are having, na? So from this formula we can directly identify the number of pairs, right? So it will be negative of G capital M small m whole divided by L, negative of G capital M small m whole divided by L, negative of G capital M small m whole divided by L. So it's negative of 3G capital M small m whole divided by L. This is an initial potential energy. Final potential energy, again 3 objects, 3 pair, U12, U13, U23. So it will be final, it will be, this is initial. Final, it will be negative 3G capital M small m whole divided by 2L. So what will be the change in potential energy? Negative of 3G capital M small m whole divided by 2L, right? Plus G capital M small m whole divided by L, right? 3. So 3G M capital M whole divided by L will get common, minus 1 minus half plus 1. Right, so it will be 3 by 2G capital M small m whole divided by 2L. This will be the amount of the work done by the external agent. Okay, this is how also, this is for this system, right? Using this formula we can calculate the potential energies. In 6th chapter, now let's come back to this point. Change in kinetic energy. Work done by external, work done by conservative, work done by non-conservative, right? That will, non-conservative forces, it means in kind of the dissipative or resistive forces like friction. In space, we are not having any kind of the friction. This will be 0. External agent, right? Plus work done by conservative, that is equal to, whenever the conservative force does the work, it is always negative of change of potential energy. So that is delta K plus delta U. This is an actually. Now, in our case, when external force, see why we took that formula into the previous case, that work done by external force is always is equal to delta U. Why? Because W external, see, work is done in such a way that delta K is 0. That's why W external is equivalent to delta U. Right? W external, that is equivalent to delta U. Right? So in this case, we are not having any kind of the resistive forces or dissipative forces. And suppose if external agent is also 0, then total energy always remains constant. Whatever the variation we are getting, right, it will be equivalent to delta K plus delta U only. This is what work energy. This is the question solving approach. Only 2 equations we are going to use. The first equation we already used. If delta K is equivalent to 0, the work is done by the external agent, right? Okay, then it is always equivalent to delta U. It is always equivalent to delta U. Okay. This is only the question solving approaches. Analysis. Example. Let's take one example. Example of escape speed, right? Example of, right, the escape velocity or speed, whatever you want to say, right? It's a different concept, but we can understand it well by using the work energy theorem. It is one of the applications of the work energy theorem. Yes, it is explained. It is explained, right, into the different manner. Separately, it is explained, but it is one of the applications of the work energy theorem. Now, what does the analysis states? Let us take an example. Object is kept surface. How much velocity it is needed to reach at the height 2r above the surface of the earth? Velocity needed to reach at the height h is equal to 2r above the surface of the earth. Question is given. No presence, right? There is an absence of the dissipative forces, resistive forces. It means simply we have to use only one equation. Total energy at the initial position, total energy at the final position. That's it. Total energy at the initial position, total energy at the final position. At initial, it was at rest, right? Now suddenly, how much amount of the velocity is needed, right? So initial kinetic energy, the velocity needed is V. At this point with respect to center of the earth, what is the potential energy? Negative of G capital M small m whole divided by R. When it is reaching to the final point, the velocity is getting 0. So kinetic energy will be 0. At the final point, what will be the potential energy? Capital M small m whole divided by 3R. This M will get cancelled. Right, so it's V square by 2 is negative of G capital M 3R plus G capital M whole divided by R. Right, so V square by 2, that is equal to Gm. Right, it's 2Gm by 3R. So velocity needed is 2 under root of Gm by 3 of R. If you are projecting the particle right from the surface of the earth with the velocity V with this value, then it is going to reach right up to the 2R height above the surface of the earth and it's going to stop. This is what the application of the conservation of energy is. Now suppose concept of escape speed, right? Concept of right escape speed. This is the surface of the earth, radius of the earth. A particle is released in such a way it can escape the gravitational field of the earth. Gone. Tata. Tata. Again, how much with what velocity it should be projected? Okay, so that's an exact definition of the escape speed, right? The velocity, right, with which the particle, velocity with which particle is projected so that it can escape gravitational field of the earth. Again, work energy theorem. Dissipative forces are not there, so K initial, U initial, K final, U final. This is an initial point, right? Final is an infinity. So at initial point, right, what we are having? We are having initial kinetic energy as half mv square, initial potential energy as G capital M small m whole divided by R. At infinite, kinetic energy is 0. At infinite we are not, and beyond infinity we are not able to define, na? Right? What is beyond the earth gravitational field? Abba dabba chabba. So this will be the escape speed, that will be equivalent to 2G capital M whole divided by R. 2G capital M whole divided by R. Right? For earth, its value is nearly equivalent to 11.2 kilometer per second. 11.2 kilometer per second. One of the applications of the work energy theorem. Concept of interstellar speed beyond infinity. Let us take an example. This is Earth. We have to send rover to Mars. Right? With what velocity v it is projected? Right? Now see, let us consider this is an imaginary boundary up to which the gravitational force of, for us this is infinity. Beyond this, we have taken the values of the 0 for escape speed, because we need to escape this gravitational field of the earth. Right? Now If you are in a school, suddenly bell rings. How much amount of the velocity you are getting to escape from school? That's your escape velocity from school. Same. How much velocity this object is given, right? But when you are reaching beyond, right, when you are leaving the gates of the school, what will be your velocity? That will be the interstellar speed. The speed of the object in interstellar space. Speed of an object right? Work energy theorem. K initial, U initial, K final, U final. K initial, U initial, right? K final, U final, right? Initially it was at the surface of the earth, half mv square, right? Okay, this is minus G capital M whole divided by R. Beyond infinity, suppose it is crossing. So in interstellar space, this is an interstellar space. Beyond school, you are having the velocity. Now let's move on to the movie. Right, that thing. So in interstellar space, we are having half mv square final. Beyond infinity, it is 0. Right? So what is interstellar speed? That is equal to under root of v square minus 2 G capital M whole divided by R. Right, this is an interstellar speed. This sometimes this is also asked, right? This is also the one of the applications of the work energy theorem. This kind of the questions are also asked. Suppose this is a planet of mass m, this is a planet of mass 16 m, right? They are separated by the distance of 10 r. With what velocity this we should be projected such that it can reach to this planet? In this case also, we are rapidly moving on to this. First of all, we need to find where net potential energy is 0, right? Okay, so in that case, this will be your initial point and this will be your final. Just apply the work energy theorem. Initial kinetic energy, initial potential, final kinetic energy, final potential, right? One of the applications of work energy theorem. You will get the answer. With what velocity should the particle be projected so that its height becomes equal to the radius of Earth? Work energy theorem, 2001. From surface, initial position, it is released to the height, final position are about the surface of the Earth. Simple calculation, right, using the work energy theorem. Right, K initial, U initial, K final, U final, that's it. Initial half mv square, potential energy G mm whole divided by R, final 0 G capital M whole divided by 2R, right? So this will be V square by 2, right? Okay, V square by 2, that is equivalent to, right, G capital M small m whole divided by, right, 2R. So V will be under root of G capital M by R. Sorry, M will get cancelled. Right, M will get cancelled. First is, if with this velocity it is projected, it can reach up to the height HR, height R above the surface of the Earth. Work energy theorem. The ratio of the escape velocity at the Earth to the escape velocity of the planet, whose radius and mean densities are twice. NEET phase 1 2016. Under root of 2gm whole divided by r, whose radius and mean densities are twice. Mean density of the planet is twice the density of Earth. Radius of the planet is twice the radius of the Earth. Consider this as equation number 1. Consider this as equation number 2. What will be the escape velocity of that planet? Under root of 2 g m dash whole divided by radius of the planet, right? Escape speed of the planet, it is under root of 2g. Mass is density into volume. Density of the planet 4 by 3 pi, right? Rp cube, right? Whole divided by Rp. This Rp is going to cancel. So escape velocity is under root of 2g into density of planet into 4 by 3 pi, right? Rp square, right? So velocity of the planet, right, is directly proportional to, okay, density under root of rho Rp square, right? So it's velocity of planet, velocity of earth, that is equivalent to density of planet, radius of planet square, whole divided by density of earth and density of earth square. Solving this, right, we are getting, right, what we need to calculate the ratio of na. So VE by VP, we are getting it as 1 by 2 root 2, right? Okay, you have to just replace the values. D will be the perfect answer. This is a question based on the escape velocity. Like this way, question based on the interstellar speed is also asked. One of the applications, right? Okay. Now, here it is one of the applications of work energy theorem. Why? Because this formula we already derived using work energy theorem, right? So, see, escape velocity is a kind of the special case application of work energy theorem, and it is, that formula is, right, derived separately. But suppose if that concept is not been taught, right, then first you need to apply work energy theorem here, then obtain the formula, and then move on to this evaluations and reach up to results. If mass m, particle of mass m is kept, Karnataka NEET 2013, height 3r from the surface of the earth, where r is the radius and m is the mass of earth, minimum speed, very nice question. Generally we are calculating the escape speed from the surface of the earth, but here a particle is, see, at the height 3r from the surface of the earth, this is the initial position of the particle. Now from here, with what velocity it should be projected so that it can escape the gravitational field of the earth? Very simple, work energy theorem, right? Right, very simple, work energy theorem. The initial point would be, right, this, and final point would be infinity. Okay, initial point would be this and final point would be infinity. So K initial, U initial, K final, U final. K initial half mv square, U initial g m whole divided by 4r. In interstellar space right now, see, if interstellar space concept has not been mentioned, right, till then beyond infinity we are not aware of any data. It means final results will be 0. If in question it is mentioned that you need to consider the interstellar space, the velocity of a particle in interstellar space, then and then your one factor will increase, one expression will increase. Just keep this thing in your mind. So this will be, m will get cancelled, right? So v square, that is equal to negative, okay, it is g capital M whole divided by 2r. Okay, so v will be, right, g capital M whole divided by 2r whole to the power half. With this velocity, if it is projected, right, with this velocity under root of gm by 2r, suppose if it is projected from the height 3r above the surface of the earth, then he can escape the gravitational field. The earth is assumed to be sphere of radius r. Okay, this you can do. Again, is a question of the escape velocity asked in 2006. So this is a homework from my side, guys. You can answer this question beneath the video. Okay, these things are there, right? This is what all the work energy theorem is all about. Okay, now let's move on. Okay, this is also the thing. Okay, everything will get into the, what we can say, this notes, right, on the app. We'll get all of those stuff into the notes on the Don't get so much worried. Okay, now let's move on to the concepts of the gravitational potential. There is a very small difference, right, in the gravitational potential, okay, and the gravitational potential energy. What it states, I told you all, work done in bringing a charged particle from infinite position to the point under the gravitational field is the energy needed for that is potential energy. But I didn't told you about how much number of masses I'm bringing from infinite point. Earth, infinite, test mass m. Work done in bringing a point mass, a single point mass from infinite position to a point under gravitational field of the earth. In bringing a single test mass, not n number. See, potential energy, we have seen the cases of the n masses. No, here only one mass we are talking about. If we are having the system, we can evaluate that stuff, but your work is done, right, by an external agency to bring that single mass. So here that work done, it is equal to change in potential energy per unit charge, right? Okay, not work done, the change in potential energy per unit charge, that is gravitational potential, and it is defined as G capital M, not per unit charge, it is per unit mass, right? It reminds us about the electrostatics. So GMM, right, GM whole divided by R. This is the formula of the gravitational potential. Same, it is applicable. The value of the gravitational potential is negative, maximum is 0, at infinite the value is 0. Same. There is only one difference, right? There is only, right, one difference. So the same point we are going to see and write into the technical terms, right? Work done in bringing unit mass from infinite position to point under gravitational field. Of Earth. Right. Now, gravitational potential, it's a very simple term, right? Sometimes, see, same like gravitational potential energy, we can define it for the system of masses, right? And we can define it. See, gravitational field we already have seen. Now we need to see the relation between the field and potential. And before that, suppose if we are having the n number of masses, suppose this is mass m1, this is mass m2, right? And suppose we are having the n number of masses situated at the distance, right? Then with see, n number of the masses, n number of the potentials with respect to the infinite. N number of masses, n number of the potentials, right? For the rigid bodies, right? This kind of the calculations, right, are there. It's a very simple data, right? We are not, okay. Gravitational field, we all are aware of, right? The spatial area up to which there is a force of a gravitational the spatial area up to which the gravitational force of the earth acts, right? Okay, so that is force per unit mass. So it will be defined as Jm whole divided by r square, right? This is a gravitational field. It is a vector quantity, okay. It is a vector quantity. That is the relation between the field and the potential, right? Okay, so that is defined as I is equal to negative of del V by del R. Right, this is the relation between this you all are aware of relation between the gravitational field and potential. This kind of the questions are asked in examination, right? I'm going to show you all in front. Okay, suppose let us take an example, right? If the potential is defined as, suppose electric field, the gravitational field is defined as, right, x square of I plus y square of j plus z of k, right? Okay, or if you want to define into the very simple terms, right, then we can define it as 3x 2y plus z of k. This is the equation of an not a gravitational field. Now in this case we need to calculate the potential, right? See, first of all I want to tell you all the potential terms never exist. There is always a potential difference. If I am saying the potential at a point, it means it is also with respect to infinity, right? Actually it is gravitational potential difference. Potential word, right, it is not appropriate because everything is with respect to infinity, right? Now suppose if we need to calculate del V, that is equal to, right, I dot del R, right, I dot del R. Okay, now we need to calculate the potential between the points, right, 0, 0, 0 to the point, right, 1, 1, 1, right? Now let's solve this using the relation between the potential and the potential energies, right? We are going to solve this stuff. Okay, relation between the potential and the potential energies. Okay, now integrating on both sides we are getting I, right, dot dr. Can I replace dr as del x of I? Okay, can we write this simply, right? Integrating the things on both sides, integrating the expression on both sides, right, we are getting V, that is equal to integration of I dot del x of I plus del y of j plus del z of k, right? Okay, now replacing the value of I here, this is from 0, 0, 0 to 1, 1, 1, right? Now replacing the point, we are here getting 3x del x from 0 to 1 plus 2y del y from 0 to 1 plus del z, right, from 0 to 1, right? So finally, right, integrating this stuff, we are getting the potential difference, right, as 3x square by 2 plus 2y square by 2 plus z, limiting from 0 to 1. So V is equal to 3 by 2 plus 2 by 2 plus 2. So V is equal to 5 by 2 plus 2, 5. Potential difference is 9 by 2, right? Okay, joule per kg. Okay, this is how things are asked. Okay, the relation between the potential and the potential energy. This is what all about is, right? So let's have the glimpse of the potential, right? One another sum we are going to see, right? Okay, circuit. Okay, no, it's okay. One infinite GP sum we are going to see. That's very nice. Okay, here it is. Come on, man. Where it is? Okay, here it is, right? Infinite number of the bodies are kept. Infinite number of the bodies are kept. Suppose see each of 2 kg. This is 2 kg. This is 2 kg. This is 2 kg, right? And this is 2 kg. They are kept at a distance, right? 2 meter, 4 meter, like this way. Sorry, 1 meter, 2 meter, 4 meter, and it extends up to infinity. We need to calculate. See, as I said, gravitational potential for the system of masses. Gravitational potential for the system of masses, right? So this is a case of infinite GP. When I'm going to calculate the potential, then it is negative of G capital M small m whole divided by 1. Negative of G capital M small m whole, sorry. not potential energy, it's potential, right? Negative of G capital M by 1, negative of G capital M by 2, negative of G capital M by 4, negative of G capital M by 8, it extends up to infinity. So you can see, right, infinite GP is formed, negative of GM, right, I'm moving on, it's 1 plus 1 by 2 plus 1 by 4 plus 1 by 8, it extends up to infinity, right? So this is the case of infinite geometric progression. Right, for this kind of the sums, right, we are having, for this kind of the series, we are having the solution as, right, a by 1 minus r, where a is the first term, right, and r is the common ratio. A is the first term and r is the common ratio, right? A is the first term and r will be the common ratio. So what will be the common ratio if you identify the series is Gm. The first term is 1, common ratio is 1 by 2. Now mass is 2. So what will be the net potential? Negative of 4G. Right? This is the perfect answer for this specific question. Two masses of M and 4M, they are kept and they are separated by distance r. From what distance, right, okay, the net potential is 0. Suppose it is in distance x and this is r minus x. At this net potential is 0, it means G capital M whole divided by x is equal to G, right, 4M whole divided by r minus x. So this is going to cancel, G is going to cancel, r minus x, that is equal to 4x. Right, x is equal to r by 5. At the distance of r by 5, the potential, the net potential is getting 0. Right. So this kind of extra terms related to the gravitational potentials are also asked. So let's have the glimpse, right, what we have seen, right, in this, right, session till now, right, and what the topics they are remaining. It's a very simple, the very simple thing is remaining. I think, yes, it's all about the Kepler's law. Okay. See, first we moved on to the flowchart of the chapter. Right, okay, yes, exactly, this is the flow chart. After that we moved on to the Newton's law of gravitation and all of this stuff, right? We saw in the scalar form, we saw into the vector form some of the noteworthy points and the limitations related to it, right? Superposition principle, right, we saw that into the vector form, right? We moved on to the sums related to it, right? And after that we moved on to the variations of the G's, of densities, latitude, altitude, right, and that, okay, everything we saw, okay, and after that we saw some sums related to it, right, and okay, gravitational potential energy, work energy theorem we saw, right, and with that we moved on with the concepts of the gravitational potential. Okay, now last topic is remaining of this session, right, and that is the Kepler's law of the planetary motion. Kepler's law of planetary motion. It's a very simple, yeah, it's a very simple thing, right? Kepler introduced, see, Galileo, right, gave one statement and he was charged for blasphemy at that time. See, in that century, church was like, I'm sorry, extremely sorry about that. In that century, some X part was, right, dominating. Extremely sorry for that. Okay, in that century, okay, I want to tell you all that very simple thing. Okay, Galileo was charged for blasphemy for giving a statement, right, about the actual position of the planets into the solar system and the sun, around the sun, right, and lots of statement is given, and for that, right, it was against some X part and he was charged for that. So in that case, I want to tell you all, right, Kepler was a person who gave then actually 3 laws, right, and who actually defined the things well, right. Okay, so those laws of the Kepler, right, see, this is what the latest thing is going on. The yellow dot is sun. Whatever the planets are there, they are revolving around this sun. Sun is also revolving around the center of the Milky Way, right. So actually whatever the earth it is revolving, it is not an circular path, right, as sun is also revolving around the right in the center of the Milky Way, Earth is also moving with that. So path is not exactly that, it's helical, but we are not able to identify that path because that point with respect to which sun is moving, it is billions of kilometers away from the Earth. Billions and billions and trillions kilometers from there, that we are, that value even we are not able to, if we have to define that into the light, millions of and billions of light years, right? Light years, yes, that's perfect. So basically there are three laws of the Kepler's. The first, Kepler's first law, it is also known as laws of orbits. Second law of motion, that is laws of areas. And the third law, the Kepler's third law, that is laws of periods. This is the third law, right? This is the second law, the Kepler's second law of motion, and this is the Kepler's first law. Now what does the first law states? What does the Kepler's first law states? It states that, right, the Earth is revolving around the sun, not into the circular path but into an elliptical one, and sun is at the one of the foci points, right? Earth revolves around sun, right, on elliptical path, and sun is at one of foci points, focus. This is what the Kepler's first law of motion states. Second, aerial velocity of Earth is constant. Now what does it state? It states equal areas swept in equal time intervals. Path is elliptical, it doesn't mean, right, things are getting changed, right? In the morning the span is of 1 hour, in the evening also the span is of 1 hour. On 1st January the span is of 1 hour. 1 hour is equivalent to 60 minutes, right? And the end of the December also, or in the November also, right, the 1 hour is equivalent to 60 minutes only, right? So in that case, right, suppose this is the thing, if this much area A1, right, this is an area A1, it is taking, right, to cross swipe this area in time T1, and suppose if this much amount of the area it is taking into the time T1, right, then this aerial velocity is constant, right? That A1 by T1, that is equivalent to A2 by T2. This aerial velocity is completely constant, right? This is not an exactly thing, right, what we are writing. Okay, A1 by A2 we can't write like this way, but we can say aerial velocity is constant, right? Aerial velocity, in another sense, aerial velocity we can write it as L by 2m, angular momentum by twice of the mass, that is equal to constant. What does the third law states? Third law states that the time period, the square of the time period of the revolution of a astronomical object around a point or a planet or a star is directly proportional to the cube of the radius. Removing this proportionality sign, we are getting t square is equal to 4 pi square by gm into r cube. This is what the, so this is the first law. What it states: Earth revolves around the sun onto the elliptical path and sun is at the foci points. Second, aerial velocity is constant. Third, law of the periods, that the time period of the revolution is directly proportional to the radius of the path, the cube of the radius of the path, the square of the time period to cube of the radius of the path. Okay, in NEET 2018, there are some PYQs related to the Kepler's law. Even, right, we are going to see this stuff. The kinetic energies of the planet in an elliptical orbit. See, there are the 3 points A, B, C. At the 3 points, we are having the 3 values of the kinetic energy, Ka, Kb, Kc. AC is a major axis, as B is perpendicular to the AC at the position of the sun as shown into the figure. Then If I'm going to tell you about the kinetic energy, right? See, L by 2m is constant. According to the Kepler's second law, L by 2m, that is completely constant, right? So in this case, can I say the kinetic energy is defined as L square by 2I? Well, R is the angular momentum of the system, I is moment of inertia. L is the angular momentum of the system and I is moment of inertia. Can I say IC is greater than IB is greater than IA, right? Where I is moment of inertia. So if this happens, then according to this equation, if I is less, Ka is greater than Kb is greater than Kc. This is the correct relation of the kinetic energy. B is the perfect answer for this specific question. B is the perfect answer for this specific. A planet moving along the elliptical orbit is closest to the sun at the distance r1 and farthest at the distance r. Closest distance is r1, farthest distance is r2. Equal area, aerial velocity is constant of 1, that is aerial velocity, right, of 2. In another sense, L by 2m, m1 v1 r1, that is equivalent to m2 v2 r2. So v1 by v2, that is equivalent to what? That is r2 by r1. Ouch. This is the perfect answer for this specific question based on the Kepler's law. The period of the revolution of the planet is around the sun is 8 times that of the B. Time period of the revolution of A 8 times that of the B. The distance of A from the sun is how many times? RA is how many times, right, of RB. Using Kepler's third law, T square is directly proportional to R cube, right? T1 by T2, right, whole to the power 2 by 3, that is equal to RA by RB, right? It means RA by RB, time period of first is 8 times the time period of B, so it is 8 times 2 by 3, right? Okay, so here we are getting it as RA by RB, that is equivalent to 2 to the power cube into 2 by 3, right? So RA by RB, that is equal to 4. It's 4 times. The fourth is the perfect answer for this specific question. So this kind of the sums are there. A very simple explanation of the Kepler's law, right? Okay. So guys, this was the end of the gravitation, right? Hope so you all like this teaser, right? Okay. The next teaser of the solids, right? It is really going to be awesome and a new thing is going to come. Okay. So the next lecture will be completely on solids and fluids, right? We are going to see the important theories in solids and fluids, like Hooke's law, right? And there's one Archimedes principle, Pascal's law, Bernoulli's equation, right? And this kind of the important stuff we are going to see in that, right? We are not going into that much theoretical part, but the important stuff related to the NEET and JEE point of view, we are going to see that Stokes law and everything, right? Okay guys, so it's time to go. Thanks. I will be waiting for all of your comments regarding this video, right? And you have to do, right, okay, beneath this, okay? So thanks a lot for this lecture. This is Indrajeet Singh signing off from the desk. Bye bye, Sat Sri Akal and Namaste from my side, Bacha ji. Bye everyone. Stay at home, stay safe, stay healthy. We'll meet again into the next lecture. Bye.